Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about cooling issues. So let's dive right into it. Now, one thing you have to understand that many people have this sort of old view where air conditioning is just a luxury. Now, depending on where you live, that may appear to be true. For example, if you live in Canada, the summer is like a winter of India. So yes, I can understand it from that point of view. However, it's not a luxury anymore. At this point in time, as Earth is getting heating up and our heat strokes are getting much more brutal. So reality is it is slowly turning from a luxury to a necessity, meaning you have to have this. So this is creating a paradox because more the planet heats up, the more we need to use this, and this leads to a vicious feedback cycle. So this creates a very serious problem, and on top of that, most of the time we are not aware of the scope of the cooling that we utilize in our world, because you will think like air conditioner, humans, office, things of that nature, while they are big, but there are something even bigger. For example, food industry. The reason why you have food at a reliable intervals, where it's like, if I'm going to go to a mall, I'm going to get food. How the heck do you think that's possible? Because of refrigeration. And same goes for medicine. How do you think we can manage this sort of pandemics and all that jazz? Again, refrigeration. Think of this: what would happen if you did not have refrigeration? Most of the medication would be destroyed by the time it reached to the patient. So significance of this sort of technology, as in refrigeration, cannot be understated. And not to mention, our whole of entirety of internet requires huge, as in my ludicrously huge amount of cooling. So we need to deal with this. This is not something that we can ignore. It's not something that's dealing with luxury. It is life-threatening kind of scenario. So we have to sort this out. So what's the problem? We do know how to cool this. We do have refrigeration. We do have food. So what's the problem? Problem is, while we do utilize heat pump, now this puppy is amazing compared to every other thing that we have figured out. For example, absorption chiller, Peltier cooling systems, things of that nature. This puppy beats all of them. Yes, this is amazing. This works. Known, reliable heat pump technology. Everything is awesome. But it does take a huge amount of it. While it is good, it's not as amazing as we want it to. So it takes a lot, as in lot of energy to run this puppy, and it dumps a lot. Now dumping part is the problem, because generally what you have is, assume it this way: your outside temperature is around 35 degrees Celsius. Now you want your inside temperature to be 20 degrees Celsius. That's a temperature delta of a little bit of 15 degrees Celsius. Your compressor is like, I got this, fam. Okay, so what it's gonna do is gonna consume 2 kilowatts of energy, take the inside heat and dump it outside. Now here's the deal: it would have taken at least like 3 or 4 times the energy from the inside of your room. That's how your room gets cooler. The energy is removed from it. It's a heat pump. It's pumping heat from inside of the room to the outside. Now while you are dumping it outside, you are multiplying that with the heat that you have, not multiplying, as in adding the heat that you used to spin the compressor. So meaning, let's say you removed 5 kilowatts of heat from the inside of the room, you added 5 kilowatt plus the 2 kilowatt that you spent on running the compressor, meaning now the outside environment has 7 kilowatts. Even though sun only added, let's say, 5 kilowatt, you put output at 7 kilowatts. So you can see the paradox is like, sun is only adding a little bit, we are removing boatload of it, and as the temperature reaches up, because it dumps so much heat energy in the environment, and imagine this multiplied by thousands of household, millions of air conditioning unit in a city, the whole ambient temperature goes from, let's say, 35 degrees Celsius to 40 degrees Celsius. Yes, this is a temperature normally achieved in Bangalore, Delhi, things of that nature. So in that sort of scenario, your COP goes down. So basically the multiplication you are doing, how much energy you can pump out, goes down. Consequence, you are still pumping 5 kilowatts of internal heat, but now you're consuming 3 or even 4 kilowatt of electrical energy. So that and huge amount of electrical energy, now putting more, and then this vicious cycle makes it ludicrously difficult, meaning you can't do anything about it. It's like the more air conditions people use, the more problematic it becomes. So this creates an issue, and the reason for that is the heat is dumped into atmosphere. The heat is not going away. That's the biggest problem. It's like, yeah, you took the heat, you took the heat from the inside of your house, dumped it outside, but where is this outside? This is the atmosphere. What happened after that? Nothing. That's the problem. It did not disappear after that. It's just like, yep, I'm staying in the atmosphere. So even though the sun's heat that you are removing, that's not a big deal, because like, sun is gonna input that anyway. Is that the heat that you added to remove it now became a hazard. So over time, now do that for every day, do that for every summer season. Now you're talking about idiotically huge amount of thermal loading onto the atmosphere, which atmosphere cannot get rid of. That's the problem. Now you may be like, okay, we are utilizing convection. Why do we utilize that? Well, it's the most densest form of heat transfer. There are other ways of converting heat away, but convection is the best. That's why we utilize. That's how something this small can dump 5 or 6 or even 10 kilowatts of heat. Otherwise there is no other system to do that. So but this does come with the consequence that heat does not go anywhere. It's like trapped. It's like you are just moving it from here to there, and then put more energy to move it here and there, then put even more energy. That the energy that you are putting yourself is the problem. So we have to look into what we classify as radiative cooling. Basically, if you studied a thermal flask in your school, you know for a fact that we put a vacuum system just to insulate that thing. Vacuum is amazing insulation, but you still get cool stuff in your thermal flask. How the heck that happens? Photons. They don't care about vacuum. They just go YOLO on it. So if you can somehow dump the energy that you are dumping into the atmosphere, you dumped it into photons, and that photon went into space, you don't have to worry about it. It's like gone. That energy is gone, removed from the planet Earth. Meaning, if you have cities that are consuming energy like there is no tomorrow, it's like going GG on the heat output, and all the heat is turned into photons, and that escapes the atmosphere, you don't even have to think about it. It's like your planet will actually start to go down cooler. So that's the problem. Convection not good enough, and the way we are dealing with it, we simply cannot continue doing this. We have to solve this. Only physical solution is radiative cooling. Basically dump in heat outside of the system being the planet's atmosphere. We have to dump the heat outside there. Where is this outside? Nowhere. That's the whole point. There is nothing in the space or surrounding us which will reflect back, so you don't have to worry about it. It's like just go YOLO. So that's the problem. So we have to understand our atmosphere, because that's what we classify as greenhouse effect. Now, most of the people are focused on CO2 because it is a very important contributor, because you have to understand this. Sunlight comes in. Now, some amount of sunlight is absorbed by the atmosphere itself. Atmosphere is not 100% transparent to visible light. That's why it looks blue. So it does consume some amount of energy and gets absorbed by, let's say, soil. Soil absorbs that photon energy. So let's say 100 watts of photon energy dumped into the soil. Soil will re-radiate it. Soil won't like to be like, in high ambient temperature. It's like, hey, I want to normalize. So soil will dump that energy. Now, because absorbing the energy and redumping it reduces your photon wavelength, so your wavelength will go from visible to infrared, and that's how planet cools itself. So basically, planet receives energy in like very high spectrum, basically anything around ultraviolet, visible, or high infrared, and then it dumps that heat slowly over time, utilizing there is a loophole in the atmosphere. That loophole is classified as basically 8 micrometer. 8 micron to 13 micrometer. Basically, if your photons are within the spectrum, it can ditch the atmosphere. Like atmosphere will not stop it. You have to understand there are other things also in atmosphere, like water vapor, which is very brutal, and then you also have other things, nitrogen, oxygen. All of them play a role. That's why planet is hot. Think of it this way: you can freeze Venus if you change the atmosphere composition. You can still freeze to death even if you have very little of carbon dioxide. For example, Mars is like 95% carbon dioxide, but it's so little it's still freezing. So you have to understand that atmosphere plays a very critical role, and in our current scenario, photons are the only way where you can dump the heat out the planet. And 8 micron to 13 micron is the wavelength how Earth cools it. So basically, sun dumps 1 gigawatt of energy, for example, and Earth re-radiates around almost 0.9 gigawatts of energy. That 1% bounces back. That's how we have ambient temperature. Everything is calm, everything is stable. But we added little bit of carbon dioxide, and the atmosphere is like, really? So that's the problem. So how do we solve it? Utilize that window. Now, if you dump GG amounts of energy here, most of it will go to space, so you don't have to think about it. Now, this is a very good demonstration of this technology. Think of it this way: you have a hand. That hand is radiating all of the photons, but you can't see it because that photon is being blocked by this plastic bag. However, if you change your spectrum, go to infrared spectrum, you will notice that hands are clearly visible because plastic is no longer able to absorb it. That's the same thing is happening with our atmosphere. Not every energy photons is absorbed simultaneously. So this window, if you dump the energy, it's like this. It's like I don't even see the atmosphere. So, and be mindful when we talk about visual spectrum, we think it's huge because again it has millions of colors. It's not huge from electromagnetic point of view. So our visual spectrum is like this. Okay, infrared is this. It's huge. So to classify infrared, we have multiple subsections in that infrared. So what I am talking about is classified as long wavelength infrared, basically the camera sort of stuff. Now you will also notice like, okay, this I can't use, this I can't use, and let's say there is noise, but I can also use this. Yes, we do use that for heat-seeking missiles. They generally utilize from 3 to 5 micron. That's how the jet engines heat sinks are captured. So you can understand that this is the biggest, widest window. So if you can take all the energy of all the air condition and channel it through this window, Earth is like, I do not notice what happened. It's like that heat disappeared. And here you can actually do this to cool the planet if you can figure out how to dump all the energy through this window, meaning the photons of long wavelength infrared system. If you can get this done, you got this rid of the energy. Right now that's the problem, we are unable to get rid of the energy. If you can somehow funnel that energy into this window, the end, we don't have to worry about it. That's the whole thing of the atmosphere. You have to understand the atmospheric window role here. So SkyCool system, what they have figured out is basically a nano photonic coating system. Basically it's a very thin coating system. Now be mindful, this option of like, Earth radiating heat away, Earth does that all the time. That's what we classify as normal. Like in the desert, as in like in early, before compression refrigeration, people still used to have ice. Same in Delhi, same in basically most of the old worlds actually used to know how to do this. How the heck we used to do that? Basically you had very thin film of water and you just let the night sky do its thing. What does it doing? Nothing. It's just like letting go of the photons. So you could literally have ambient temperature of, let's say, 10 degrees Celsius, but your ice will freeze. Basically water will freeze simply because it can dump so much energy that it will go to zero. Again, be mindful, it had to be very thin. It cannot be like, deep. You cannot have 1 foot of water and it will turn into ice. That's not gonna happen. It has to be very thin. Now it used to be done like, that's how we used to make ice, but now we no longer do that. We use refrigeration. Now we have to do the same effect, dump the heat away from here. It's like, go away heat, we don't want that back. Now biggest issue with that's called nighttime cooling. In the daytime, sun dumps way too much energy into you, so that's the problem. So basically you created a panel, inherently this every panel, everything that you build, like a metal sheet or everything, it's also dumping heat away. There is no something that is not doing that, but problem is sun can overwhelm it. Basically you put this panel, it's like, I'm gonna utilize this for cooling. Sun is like, I'm gonna cook this puppy. So how do you make sure you don't get cooked? Coating. Now this silicon specific coating does something very interesting. From a sun's point of view, this is like a mirror. If sun is looking at it, it's like tweet. It's like bouncing back. It does not care. It's like from sun's vantage point of it. That's why from your side, if you look at from side, it will look like a blackish thing. But from sun's vantage point, it's absolutely like a mirror. It cannot turn it. It's like a two-way mirror. So you have a mirror, sunlight comes in, sunlight, nope. And here's the deal. The fluids that are traveling behind this cooling panel, they can dump their photons. That's the amazing aspect of this technology. It's like sunlight out, photons out. That's the whole point. It's one-way check valve, quote unquote. So sun cannot dump energy into the system, but it can dump energy out of the system. And because of the wavelength it is specifically chosen, that's the whole point of this. It's only let that spectrum out. You can literally have this panel in the broad sunlight, as in like Indian sun, as in like around 50 degrees Celsius. This puppy will still get cold. And they can drop below ambient temperature. Be very mindful. Evaporative cooling, while it's good, then why don't we use it? That's the whole problem. It does not go below ambient temperature. So if your ambient temperature is 30 degrees Celsius, yeah, it's gonna evaporate to like a little bit less, but it's not gonna go cool. And again, you also add way too much humidity, which creates the situation even worse. Here, you can actually go below. Let that sink in. Below ambient temperature, because from sun cannot deposit energy into this. That inherently makes it cool, and it can also allow energy to escape into the atmosphere or directly go through space. So that's the amazing aspect of it. Now this can work in day and night. Night is amazing, daytime is also amazing, but it does have a consequence. I specified water vapor also plays a critical role. So if you have a cloudy day, foggy day, things of that, basically if you have water vapor is like, you shall not pass. So that radiation simply cannot go out. Now this puppy will still work, but it will not be as efficient. So meaning if the cooling capacity was like, let's say 5 kilowatts, it will drop to 1 kilowatt, but it will still work. So idea is you're gonna have solar that's gonna provide your main system, and this is gonna be auxiliary system for your cooling system. So this works. This is a known technology, and known as in like recently known. This coating was recently developed, recently mass manufactured into testing. Right now it's on a testing phase, and they have achieved real world, as in like somebody actually built it, somebody actually deployed it, somebody actually using it to cool their data center, somebody is actually using this is from their grocery store, and they are getting 10% energy saving. Now you may be like, wait a minute, I hyped this puppy up this much and it's only 10%, because it's Gen 1. And not to mention right now efficiency is one of those things that you cannot predict in lab. On lab everything is like 99% efficient, but the moment you make it in real life, it's like, wait a minute, that's it. So that happens. Now again, the company has a good foundation, and 10% may not sound significant. Tell that to a freaking service center runner who is like running giant server farms. They're like, shut up and take my money. That's how significant that. Heck, even for a household, if you're like, think of this way, you add this solar farm, it will reduce your electricity bill for 10,000. Unless that panel is not too expensive, everybody will do that. 10% matters. And not to mention the energy that is dumped utilizing this puppy is outside of the planet. You don't have to worry about it. It's not like heating up the system. So for example, let's say some people who have luxury of space, they have like large amount of space, they can literally cool their whole system utilizing this only. Right now it's not very efficient for a single household, but it can be done if you are like, you know, off-grid environment where you have a lot of surface area. You can do this. Like you can be like, hey, my whole house is passively cooled, I don't even have to think about air conditioning. It's like I don't think about it. So that's why the foundation of that technology, this coating, is good. It is being proven in real life, in real world, and it's actually showing a lot of promise in real world. I'm like, that's why I specified very realistically 10% in real life is a lot of money for big industries. If you go to any grocery shop, it's like, hey, how much will you pay for, like, you know, saving that 10% of energy bill per month? It's a lot of money. So what we can expect in the future? Well, this is one of those things that you may think is just like for dumping energy, but here's the, it is a completely reflectant to sunlight. What does that mean? That simply means if you put a very thin coating of this on top of solar panel, it will stop solar cells from heating. And if you fine tune that puppy properly, basically solar cell does not use 100% of the solar spectrum. Otherwise it will be like absolutely black and it will be absolutely cold if it actually did that. It's not. So what if you utilize this sort of coating to remove heat that is gonna heat up the panel? It's like, hey, panel, you're not gonna do anything with this photon, let me reject it. If it is done, their early estimates is you can easily expect increase the output of the cell by 5%. Now, like, again, they are not tampering anything with the cell, then why the heck output will increase? Because it's no longer heated. If you look at the back side of any solar panel, if you pay attention, they're rated at a like stupid temperature, as in like 25 degrees Celsius. I'm like, where in India are you gonna find 25 degrees Celsius? It's like, who the hell came up with this? I'm happy that Indian government is slowly forcing them to move to 30 degrees Celsius. It's like, yeah, the energy output goes down drastically if you heat from 25 to 30 to 35. It's like in India, it should be around 40 degrees Celsius at least. And yes, real world temperature I'm talking about. I'm not talking like some freak accident. Like this is normal temperature for us. 30, 40, that's like, we don't even care about it. So in those sort of scenarios, if the cell is not heating up that much, it is giving you a lot more power. It's gonna last much longer. So after, let's say, 20 years of lifespan, it will still have much more useful power compared to a non-coated system. So there is a lot of secondary advantage of that. And if right now this puppy is acting as a heat sink, basically it's just you're dumping heat into it. It's just like, leaking it off, like wicking it off would be correct way to say that. But what if we figured out how to dump energy into that, meaning let it glow in that spectrum, basically like a flashlight or floodlight. It's like glow. What if we can dump so much photon in it, like how we are dumping energy from inside of our house to outside utilizing compressor? If we can do that, something like of think of it this way, something that absorbs the heat that our condensers are giving out and converts that into that exact spectrum, like an inverse of not inverse, I think like exactly same thing as what we have utilized for our LEDs. LEDs are basically monochromatic, they do not have color, they cannot be white. So we have blue LEDs and phosphor coating. That phosphor coating creates like blue photons into red and green photons, something like that. What if we take something like high intensity infrared and convert it into that exact window? Amazing things can be done. So right now we do not know how to pump heat into it. That's why the output is so weak. But again, even at a weak output is still good because it will drop your temperature below the ambient. So it's desirable enough right out of the gate. And if somebody figures out, because the moment this technology started to get a little bit of traction, hundreds of other engineers also started to come out, hey, I also have this idea and this idea. It almost created an avalanche of system, because sometimes it happens, like, if somebody shows that, hey, I'm not stupid, other people are like, hey, wait a minute, I also had something like this, I'm also not stupid. So it happens. That avalanche is amazing at this point in time. A lot of people are pouring their money, and this is the only known way within physics where we can keep cool of this puppy. And this puppy matters to all of us, I guarantee it. So that's why if we really figured out a way to dump energy into this window, we can cool the planet. We're like, I got this. That's awesome. And it's also really useful for everything. For example, from water treatment to industrial plants. Think of this way, industrial plant dumps insane amount of energy into the atmosphere. What if they do not do that? You do not want to live near an industrial plant simply because it's just hot. Like, I'm not joking, like they're literally hot. So in those sort of scenarios, like, what if it's not hot? What if it's like the energy is just removed from the planet? It's like gone. That energy will never be brought back to us. So those are amazing things. And again, at this point in time, they need to figure out mass production, because saying like we have one data center, we have one grocery store, that's not good enough. Now be mindful, this is early stage. Same thing happened with solar panels. Like, we have satellites, we had one White House buildings. That's a good starting point. After that you go to, full mass production. So I'm happy with that. I'm seeing a lot of potential into this, and even if this design itself does not work out, other people are putting their money into it, and with other designs, so there is some chances somebody will crack it and we'll have to a cooler future. We will head to a cooler future. So the tuning is needed and better heat flow. Once we figure out how to dump kilowatts of heat per square meter, then we're gonna have some serious cooling without any side effects. So that's the amazing aspect of it. So this was our presentation on basically radiative cooling. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me your disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.